Today, I wanted to discuss this really cool equation that I saw a long time ago as an undergraduate studying mathematics, and I thought it was the coolest thing in the world. So, we all know, or well, I knew at the time, that we had this weird imaginary number that has this interesting property that if you square it, you get -1. So this is like a weird, cool, new thing at the time that I had no idea how it worked when you try to relate it to other kinds of mathematical equations. What happens if you add complex numbers or multiply them, or even, in this case, exponentiate by them? What does that even mean? And at the time I said, whoa, this is so cool. If you take I, raise it to itself, you get a real number. So I went to work. I saw this. I said, "Oh, I've got to prove it. There's got to be a nice, easy way to prove it." I eventually found my answer, and it was using Euler's formula. So how do you prove this using Euler's formula? Well, let's see. If we if we take some time and try to figure out, well, can we write I on the right-hand side by choosing a specific value for x? And it turns out you can. You can say that if x is pi over 2, then the right-hand side is I, and the left-hand side becomes e to the I pi over 2. So then, well, this is easy. If we exponentiate both sides, raise both sides to the I-th power, well, we end up multiplying I by itself, which this handy formula tells us that that just gives us -1 in the exponent. So e to the minus pi over 2. Great. I have proven the formula that I saw, or the equation I saw online. But then I got to thinking. I said, hey, I used Euler's formula for this. And I know that cosine and sine repeat if you shift x by a value of 2 pi. So there's something weird going on here, because if I repeat this proof, say, you could write, you could choose x equals pi over 2, but you could also say choose x equals 5 pi over 2. That'd be equivalent to just going pi over 2 counterclockwise and then just going around an entire circle. You still land on I, so the right-hand side of that equation is still I, but now the left-hand side is e to the I 5 pi over 2. Let's do the same thing we did before. We raise to the I-th power, and I times I is again -1, so we get e to the minus 5 pi over 2. But wait, these two numbers are not the same, so not equal. So what's going on here? I to the I should be the same, so these guys should be equal. But if you go down this way, you get a different answer than if you go down this way. As an undergraduate, this blew my mind. I thought there was a mistake in mathematics. It all had to be torn down. I talked to my professors. Turns out there's just a little bit of stuff I didn't know. And later on, when I was learning complex analysis, I realized that this is the reason why we learn about these really complicated things called branch cuts. Oh, misspelled analysis. There it goes. So we learn about these things called branch cuts just specifically to avoid weird situations like this. Because now I'll skip a few details here. When you exponentiate by a complex value, you are implicitly need to define something called the complex logarithm. So what is log of z, where z is some complex number? Oops, there it goes. So what is this? Well, it turns out that there's no nice way to define it for um, all z. In fact, if z is negative, there you can't define it. But also, you just can't take, if you try to vary c around the complex plane, you run into these problems. in which branch cuts become necessary. And that is ultimately the reason why this analysis um, gives you two different answers going one way or another. In this way, I've chosen a specific branch cut to define my function of log of z, versus this way, I've chosen a different branch cut to define my value of log of c. And I didn't know this at the time, but I think this is a really interesting way and a really interesting example to show why branch cuts are important in mathematics. Anyways, so, you know, the claim that is claimed in the online memes, online pictures that I've seen, this is true if you pick a specific branch cut. Not always true, not necessarily true. Depends on how you define logarithm on the complex plane. Anyways, that's all I really wanted to discuss today. It's a really cool, interesting example of why branch cuts are important. Thanks for listening.